Wasabi guys, in this video I'm going to do a tier list on speed integration techniques. So in this video we're just going to be judging based off on how satisfying and how cool these techniques are. So let's go ahead and get right into these techniques. Now there are like 48. I realize I'm missing one, but it's okay. But here, there's 48 pictures that represents techniques. Some of them I haven't showed you in the training yet, so I'll just give you like a brief version of that. But don't worry about it. But other than that, let's get into the first one. We have the SpongeBob looking picture. This is Caveman. Caveman Trick is this popular integral that we all know. Right, let's say like if we want to avoid partial fractions because this is nasty, right? We don't want to do partial fractions on this. So instead we let the entire exponent out of the cave. So we got x to the power 4. Now we have x negative 3. This is the Caveman trick. So here we go ahead and let u equal 1 plus x to the negative 3. Then du is equal to negative 3 x to the power of negative 4, which is what we have. And so it becomes like a simple du over u. So this is the Caveman trick. And the Caveman trick it's not always in this format. We can always have it like, it can be something like square roots and stuff, and you can like factor out the x out of the root. And then if it was like a function, it would be like an Undertow technique instead. But yeah, that's all Caveman. Cool. Just a brief summary. The Caveman trick, it is satisfying, but it's not as satisfying as the other ones, I guess. I'll probably put it in B. I'll probably put it in B because it is satisfying to like dodge partial fractions. I think this is advanced trig substitution. So good examples like this. Like 1 square root of x. Yeah, that's a very, very good example, right? Advanced trig substitution, you would do more than just the sine, secant, or tangent theta, right? Here we would use sine square theta, and that would help cancel out a lot of things. This would be like cosine theta times, and then dx would be 2 sine theta cosine theta. And then with 1 minus sine theta, right? And then cosine square, you can use that and turn it into 1 minus sine square to factor that out. So you end up with like 2 sine theta, 1 plus sine theta. So this is advanced trig substitution, where you do out of the you do more than just secant, tangent, and sine theta. You do more than that, right? You would do like cosine 2 theta or something else, right? So that would be advanced trig substitution. It is satisfying when you have a nicer trig, but that's not always the case sometimes. But I feel like after like doing it a while, like a lot of times, like doing this a lot, it's just kind of like, it's normal. So I'm gonna go with B. Definitely more than Caveman. Here, I have not explained this. This is... Do I want to save this for last? I guess I'll show that too. This is Ahmed's substitution. Let me actually... this one I have not shown you guys this one. So whenever you have like an ugly function, let's say like from A to B, we have like 1 over f of x, inverse tangent of like 1 over f of x dx. Something like this. If you have like a nasty integral that has like this or something like this, somewhere in around your integral, what you can do is you can let this integral become a double integral. So what you would do is from a to b, you will let this whole function, this portion here, you will let this equal from 0 to 1, and it would be dt. You would use the variable dt, then put the dx out, and then it would be t squared plus, and then your function squared. And then you go ahead and integrate from this, which makes the integral easier. You can interchange and then solve for dx and then dt. So this is Ahmed's substitution. It's very advanced. I don't teach it in advanced integration bee training for a good reason, because first of all, you'll never see this. This is like Olympiad level integration bee stuff. But you'll rarely, I don't think you'll ever come across this. Unless you're competing at like some Romanian competition. But this is Ahmed's substitution. Now, this is satisfying to an extent. It is satisfying if you actually do get a very nice integral, but it doesn't always turn out that way, realistically. So, in my opinion, it might either be B or A. I don't know. It is a very cool technique, but rarely will you ever get a nice integral out of it. I'm going to put B. I'm sorry. But to be honest, you rarely get like a nice... It does give you an easier integral when you do Ahmed substitution, but it's still a hassle to deal with. I'll put it to B because it's not always the case where you get a nice integral. This here, I think this is just area of a partial circle. You all know what this is, right? The area of a partial circle. It is actually kind of satisfying, I would say, especially when you utilize symmetry with it. It's very nice. Speaking about symmetry, satisfying. Okay, that goes in A tier. Okay, symmetry is so useful, especially when you deal with ugly integrals. You do like one step, it's like, oh, I can just turn this into this. It's like, ooh, and it becomes very nice. Okay, so symmetry and area partial of a circle, very nice. Beta function, it's alright. I'm probably put C. It's not really that satisfying, honestly. Beta function's really not that satisfying to use. I mean, if you like gamma, then you will definitely love beta function. But it's more of a just kind of a... I guess it's like more of like Euler's reflection, for like if you really love using that. But to me, it just becomes of a hassle most of the time. So I'm just gonna put it C. British substitution. Let's recap what this is. British substitution is when you let u equal 1 minus x, 1 plus x, or the other way around, or literally any like rational function or something, I don't know. But these are like British substitutions. Again, you'll rarely see it in integration bee, but it is kind of satisfying because it does turn out to be like a very nice integral. I might put it C, and the reason is because finding the du is also a hassle. Right? You let u equal this, but then you have to find du. I think it's just me though. I'm just bad at quotient rule in my head. I can't do mental quotient rule with rational functions. I can't do that. Or rational polynomials, sorry. Like I can't do that in my head. So probably, I guess, it would be fair to say B tier. I guess I'll put a B tier. Because it does come out to a nice integral. It's just finding du is a hassle. What is this? Oh, it's Chebyshev. I think this is Chebyshev Caveman. Chebyshev Caveman. Let me put this back down. Chebyshev Caveman. What is the difference between Caveman Trick and the Chebyshev version of Caveman? Chebyshev is a lot more advanced and one of those Olympiad level techniques that you'll never come across. Otherwise, I'm sorry, but it's pretty much this. It's one of these things. To those who are G-main students, or you have to study G-main, they do throw this at you, unfortunately, so I'm very sorry for all of y'all. But I wouldn't put in too much work on this, because this is just, it's annoying. It's a very annoying integral. But pretty much, it's the same process you do the Caveman, but Chebyshev are like the harder kinds, where you have to do the, it's one of these like formulas. How does it go? It was like P, you have like a function that's like m over n, something like that. And then they select, if you have the following conditions, there's like 3 conditions, and then it tells you like if you're conditioned this, then use u equal whatever, depending on p, m, or n. I think it's called the Chebyshev binomial integral formula, but pretty much you just factor out 4, right? You get x, and now you have like x to a negative 4 plus 1, and then now you have x cubed, multiply x cubed top and bottom, you get this. And then if you let u equal x to the negative 4 plus 1, you pretty much have a Chebyshev Caveman case. So this is now, that's disgusting. It is nasty. You have, oh no, wait, did I do this wrong? I don't even know. And like I said, I don't teach this technique. It is horrid. It's horrid. But then you have 1 plus 1 over u. Ew. Nasty. Oh god, yeah. Whatever, you do whatever with this. I don't know. I messed up somewhere. But search up, it's called Chebyshev binomial integral trick. And I know G-main they do this rarely, but they'll give one of these, and it's it is evil. But yeah, this is the Chebyshev binomial. The Chebyshev Caveman Trick. Yeah, I'm sorry. U or D. Okay, it is that nasty. Complexifying the integral. This probably B. Definitely more satisfying than beta function. But I'm put it to C. I'll put it to C because it's a hassle. It is. Unless you're like a complex algebra Olympiad and you love complex numbers, then you can put it somewhere here, like A or B. But I'm not a fan of complex numbers. I suck at complex algebra Olympiad stuff. Constructive Feynman Trick. Well, we gotta do Feynman Trick first, right? The Feynman Technique, it is nice. The reason why I don't want to put in A is because it's like a lot of the times it's not that satisfying. Okay, maybe it is kind of satisfying. It's just it's kind of a half and half. Half of the integrals that require Feynman Technique is like Weierstrass Substitution. If you've seen my Advanced Integration B series with Feynman Technique, half of it is like nasty. Nasty to speed integrate. But sometimes it is, half of the times it is also nice. Now I'm thinking I probably should just go like this. Yeah, I'm sorry. Feynman Technique, it's not, to be real with you, when it comes to speed integration, it's not always like the best. It's not always the best because of that. It's annoying to use Weierstrass Substitution. Okay, and speaking of Weierstrass Substitution, this goes here. I'm sorry, but it's a hassle. constructive Feynman technique. It is a lot nicer. It is more satisfying. Well, actually, I'll put it here because constructing Feynman technique, being able to construct an integral and then deriving it, it is actually quite satisfying. A lot more satisfying than Feynman technique. So constructive Feynman technique is probably going up there. Like a good example would be like from 0 to, I don't know, pi over 2? I'll do pi over 2. ln square of tangent x dx, right? So instead of using Feynman technique, we'll do constructive Feynman, meaning that instead of utilizing this integral, we're going to construct our integral out of the blue by letting I of n, let's consider pi of 2 tangent of x over n. Sorry, tangent of x to the power of n. And the reason why we do this is because if you notice, if you derive it with respect to n, then you get this ln of tangent of x. And then you'll notice that, oh, okay, so this is technically double derivative of I of, and then 0. And then you just solve for this, finding these, or finding this. Okay? This is inverse tangent of f of x. Inverse tangent of f of x. This is what? I need my notes. Oh, Coxeter. Coxeter Substitution. I don't know how you pronounce the person's name. I'm sorry. Coxeter? 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 I don't know. But this is Coxeter Substitution. Let me demonstrate this one, because this one isn't one of those I haven't shown you. Coxeter Substitution. It's spelled like this. Okay, this is what I'm going to demonstrate. Coxeter Substitution. Let's say you have an ugly integral. You have an ugly integral where you have somewhere along the lines of inverse tangent of a function. Okay, it's pretty much similar to Ahmed's substitution. So if you have like inverse tangent of f of x or something, pretty much this all around your integral, whatever, what you do is you let this, you turn this to a double integral, and you consider an integral from 0 to 1 of f of x 1 plus f of x squared t squared. This is dt dx. Okay, this whole portion here is inverse tangent of f of x. And so that's what you would turn that into, this integral, and then you interchange the bounds, or you interchange the integral and then simplify it to solve it easier, and then solve for dt. So it's the same, similar to Ahmed's substitution. It's just different inverse arctangent substitution. So again, very advanced. You'll never come across this. Okay, this is some like Olympiad level integration, and you'll never come across something like this. But this is Coxeter substitution. Is it satisfying? Yes, but it is a hassle. I would say I'd put it below Ahmed. Ahmed's substitution is a lot nicer to handle versus Coxeter, but they're both a hassle, and it's rare to simplify it into a nice integral, but not always. You still get like a tedious integral to handle. Solvable, but just a hassle. Who is this? I'm trying to remember. This is this Euler? Oh, Euler substitution. Okay, Euler substitution. I use Euler dodging. I'm sorry, not exactly Euler sub, because it's kind of nasty or tedious. But Euler dodging. In terms of speed integration, this is Euler dodging. Euler dodging, I would say A, but I'll put it like the last, because it's only the hassleness is just finding du. That's it. It's like Brita substitution, where it's a hassle to find du. Same goes for Euler substitution. So let me show you Euler dodging. Euler dodging is pretty much a term of pretending to know what you're doing. It'll make more sense if I explain residue dodging, but Euler dodging, pretty much we only do it when we have a radical, something like this on the bottom, right? If you want to do full out Euler sub, that's like doing integrals like this, right? But we don't do that in speed integration. We would just do like Trig-Substitution, because Euler substitution is nasty. Okay, and it's a pain to memorize, so we don't ever like use Euler sub with this. We just go straight into Trig-Substitution. Here, whenever you have something like this at the bottom, it has to be at the denominator. It has to be at the denominator. We only do Euler sub when stuff like this is at the denominator. And that's where the term dodging goes, is because you're pretending to know Euler substitution, but you don't know the full Euler sub. So Euler dodging, we just use, the typical x plus square root of x squared plus x plus 1, and then it actually, what it does, it cancels out this whole thing, and it turns into like du u squared minus 1, or u squared plus 1. And it's very nice. It is very nice. That's Euler dodging, right? So you only do it when you have like something like this, like a square bx plus c, ax squared plus c, or with like x here, right? We only do this when it's at the denominator. Okay, and that's Euler dodging. So pretending to know Euler sub, but we don't fully know it. We're just using it just for certain cases. And Euler substitution, a lot of the times when you do Euler sub or Euler dodging, sorry, in this context, it'll always turn out to like a very nice rational function, or like a very easy integral, like arctangent or arctanch or logarithm, a simple log integral. So for that, it's nice. But I put it at the back because finding du is tedious. I hate finding the du, but that's okay. It's not too bad though. It's just quotient rule, but it gets exhausting sometimes. Okay, this is force U substitution. Force U substitution will always be A. This will always be satisfying. Forcing a U sub will always be satisfying. A good example is like this, 2x minus 1. This will always be a satisfying force U sub. Forcing a U substitution, right? This is u squared plus 1 e to the 2x, 2u du is equal to e to the 2 of e to the 2x, u squared plus 1. You're just forcing a u substitution, so dx is equal to du over u squared plus 1. And so you end up with like u squared over u squared plus 1 du. It's a very nice integral. Okay, so force U substitution is super critical, super crucial. You see this everywhere in integration B. So force U substitution, A, top tier. But is it S? It's not as satisfying, I guess. It's not as satisfying. Maybe S, like very back, but I'll put it A for now. Factorial. It's nice. I guess it's satisfying. It is satisfying to use the factorial. But is it cool? It's not the coolest. Now I think about it, it's not as cool. It's not the coolest. Now I think about it, it's satisfying but not the coolest. I'll put it here. I'm rearranging now. I'm starting to second guess my thoughts here, but no, don't get me wrong. These techniques are cool, but it's you have to think about it like when utilizing it realistically, like it's a hassle. It's a hassle, and so that kind of downgrades your satisfaction. Cool technique, but sometimes ugly when applying it. Glass's master theorem. Oh, S tier. Don't get me wrong. Glass's master. This is a lifesaver. Let's be real. This Glass's master theorem is a lifesaver. Okay, like let's be honest. Without the Glass's master theorem, it would suck to solve this. It would just suck to solve this. Okay, like you would just have to do like advanced square technique. But why do this if you just do the inversion, turn this into x squared, right? And then you just turn this into, this becomes like 2 plus x squared dx, and you get like what, pi over 2 root 2, something like that, or 4 root 2. I don't remember, but somewhere there. But it could also apply to like nastier ones. I can't think of it on top of my head. What's a good one? I can't think of a good one. But there could be nastier kinds, and then you just use Glass's master theorem, and it becomes like, oh, it's just simply x squared plus x plus 1. And then you do whatever, you do the whole jig, whatever. That's probably a wrong answer. I don't remember. But somewhere along the lines. Yeah, that's Glass's master theorem. That's S tier. It is very satisfying. Okay. Heaviside Method? I mean, don't get me wrong, it is nice. It's nice to use Heaviside Method, but it's not always the case for partial fractions sometimes. Hyperbolic, converting hyperbolic into exponential form. A D tier. D. I'll put a D tier. It's not that cool. Okay. Hyperbolic substitution. This, I probably would have to put... I'll probably put it behind beta function. It's nice, but it's not like the coolest. What is this? Oh, integral recursion. Oh, no, that's D. I'm sorry, but integral, I honestly hate integral recursions. I'll put it next to. It is cooler than hyperbolic. I'll say that it's cooler than hyperbolic, but it's integral recursions are just we don't do that here. We don't do that in speed integration. Okay, for those who haven't seen integral recursions. A good example is like pi over 2. You have sine of n to the x, right? Let's say you want to generalize an integral because the integral that they gave you is has a high number. So you let n equal that high number, and then you have this integral generalization. And this is now I of n. You would call it I of n because that's just your label. You'll see why. And then you do like a very common example is like integration by parts. And so you would do like, oh, this is sine of n minus 1x, sine of x, and then this is now like n minus 1 sine of n minus 2x cosine of x, negative cosine of x. And then you have like, oh, okay, so I of n is equal to sine of n minus 1x, negative cosine of x plus n minus 1 of 0 to pi over 2. You have like sine n minus 2x of cosine square And this cosine squared becomes like 1 minus sine square. So now you have like n minus 1 pi over 2. This is now like sine of n minus 2x minus sine of x. I'm sorry. Pretty much you get the whole gist. You get the whole gist of this, right? I of n. You get like an integral recursion. You get a recursive formula pretty much. Like a sequence formula or a sequence equation. You know, like when you get things like a of n is equal to like a of n plus 1 plus a, or whatever. This pretty much you're doing that with integrals. That's literally what you're doing. And this is like what, n minus 1. This is now equal to I of n minus 2 minus n minus 1 of I of n. And then you add this here, and then you get this whole integral recursion. Yeah, that's ugh. We don't do that here. We don't do that here. Okay, it's too complicated. It's very complicated. Some people likes it. I generally don't like it, and I don't teach it because it's complicated. It's nasty. I'm not a fan of sequences or sequence recursion formulas like that. So that belongs to D. Inverse jailbreaking. Oh, jailbreaking is, this is somewhere here. It's very cool and it's amazing. It is nice. I might have to, maybe this might go S tier. It's satisfying. It's very cool, and yeah, the integrals are nice. So let's do an example. Right. Let's say, what's a very nice example? Ah, yes. Would you like to do power substitution or integration by parts? Or like what would you do? Right. Instead, well, you would probably think, oh, let's do a force U substitution. Oh, let U equal this whole thing, and I get like secant 4 of ux, and then you do the whole dx thing, and you have to derive this, and you get like secant 4 of u tangent of u, right? And then you end up with an integral of like 4u, and you have to do like integration by parts. Yeah, no, we don't do that. Okay, that's only if you're a masochist. But here we do inverse jailbreak. So we will use. Let me color this in green actually. We will use the inverse function. In which case we know this is secant 4 of x. Okay, and then plugging in 4, we get like square root of 2. So inverse secant of square root of 2, that's like what, pi over 4. And then plugging in 1, inverse secant of 1 is 0. And so our answer, so if you remember, the formula for f plus f of a, f of b, of the inverse, this is equal to b times f of b minus a times f of a. Now, we are going to utilize this formula. We're utilizing this formula to solve for this, right? If you have an ugly integral, if the inverse is nicer, do inverse jailbreak. So we are jailbreaking ourselves out of this ugly integral. So to get away with this, we perform inverse jailbreak. We know that this is, okay, based on that formula, this is equal to pi minus 0. Okay, so to solve this integral, this is equal to pi minus this nice integral, secant 4. That's very nice because we know, oh, this is like 1 plus tangent square x, which we know this is like pi minus from 0 to 1 of 1 plus u squared du. This is pi minus, what? This is like u plus u cubed over 3, 0 to 1. And so we get like 1 plus 1/3, so we get 4/3. So I guess our answer is pi minus 4/3. Is that the correct answer? I don't know, but I think this is our answer. Pi minus 4/3. Yeah. I think the 4/3 comes from like when you do integration by parts and you get like some rational polynomial. I'm just trying to double check my answers. Hopefully I didn't do anything wrong here. But yeah, this is how you would do, and look how fast that was, right? It's amazing. This is the speed integration trick. So inverse jailbreaking is very nice, very satisfying, right? The inverse function becomes a better integral. Inverse jailbreak, and that's S tier, because the majority of the times it's like it becomes a nicer integral and you get to solve it quickly. Very satisfying, and it's very cool. Okay, U equals 1 over x, inversion. Very cool. It is satisfying to an extent. I'd probably put it here with B tier. U equals 1 over x. There are sometimes I'll put it with here. There are some times when it comes to like advanced integrals, when you do U equals 1 over x, it's not always satisfying, because realistically, I mean, don't get me wrong, it's a very helpful technique, but when it comes to things like Arabic style integrals like ln of x, and you get something like this, right? And then you have to do, you like manipulate, oh, let's use 1 over x, but only for the sake of changing the bounds to like from 1 to 0. So you would split this to like, what, 0 to 1, 1 to infinity, and then you use this on this integral to get this, or whatever. And then you have to use like some Taylor series. It's nasty. It's nasty. It gets nasty real quick. So realistically, I mean, inversion is very helpful, but when it comes to like upper level integration B, it's a hassle. So I'm afraid I'm gonna have to put it here for the sake of realism. Or maybe I'm too harsh. Maybe U equals 1 over x. It is more. I'll put it next to Feynman Technique. It is a lot helpful. It does convert an ugly integral to a nicer integral, but it's still a hassle sometimes. Speaking of which, Ninja Substitution, I might have to put it here because letting U equal negative x is very nice and very satisfying, and a lot of the times the integrals does become nicer. Actually, I might put it up here next to Symmetry. Yeah, that looks a lot more reasonable. Yeah, it really is pretty much like the next level Symmetry integration trick. King's Rule. King's Rule, it's nice. It is nice. But is it the coolest? Probably, I'll probably put it up here. King's Rule. Queen's Rule, I would probably put here. Advanced Trig-Substitution, I'd probably put it here next to Advanced Trig-Substitution. Queen's Rule is where shit gets real, right? King's Rule, it's like, oh, you just based on the bounds. Okay, you just change it to a nicer integral. Queen's Rule is like, you better know your trig manipulation so that whatever you add with an integral, it cancels out. So I'll put Queen Rule here because it's very satisfying, especially with trig manipulation. It's very satisfying to cancel things out. Okay, Korean substitution. Let me show you that one. Korean substitution derives from, if you remember the secant secant trick, right? Letting U equals secant x plus tangent x, if you remember this, right? So this is the secant trick. You let U equal secant x plus tangent x, or somewhere similar, plus or minus, whatever, right? But I'll just do plus for now. Then 1 over U is equal to secant x minus tangent x, okay? And this is very nice because then you get like 1 plus U is equal to 2 of what? Secant x, right? And now you can substitute this in, right? Du is nice because the derivative of this is equal to U times secant of x, right? Very nice. This is the secret trick. Korean substitution is like a Trig-Substitution version of this. But it's nicer to not do Trig-Substitution. So, in other words, this would equal, you let u equal x plus the square root of x minus 1. Then, 1 over u is equal to square root of, is it this way? Yeah. That's correct. Yeah. Okay. So it's pretty much a Trig-Substitution version of secant x plus tangent x. A Trig-Sub version of the secret secant trick, except that you don't have to do Trig-Sub. You just leave it like this, and it's already nice enough. Okay. There's some manipulation. There's some advanced versions as well where you can actually handle this in terms of u. There is some advanced versions. Sometimes even like cube roots. It gets crazy. But like I said, I don't teach it because it's like you'll never come across it. There was one integral from MIT, integration B. It was like this, something like this, and it was like pi, something like that, or 2022 pi, something. I don't know, but there was an integral like this in MIT integration B, and you use Korean substitution. Okay. So that is Korean substitution. Now, where does this belong to? It's very cool. I'd probably put it. It's a very cool integral technique, but I might put it at the back of A. It doesn't always become a nasty integral. It's just, can I judge based off like how common the integrals are? I don't know, maybe I can't. That's a little too harsh. But it is very satisfying, I will say. It's very satisfying to do it. Is it more satisfying than secret trick? I just realized I don't have that here. It's okay. But is it satisfying than the secret trick? Probably, I think it is. I think Korean substitution is more satisfying than the secret trick. So I'll put it in A. It is a lot more satisfying. And the integrals do come out very nice. Laplace. The Laplace trick. Laplace tricks. These are, I honestly find them satisfying. So I might put an S. I might put an S tier. I genuinely do like the Laplace tricks. I really do. It does turn out very nicely. I really do genuinely like Laplace tricks. So I might have to put S tier on that. Okay. Very, very nice. There's so many Laplace properties that you can use with it, and then it just makes speed integration so much faster. Okay, if you know all your Laplace properties and Laplace tricks, you are at a level of deadliness to the competitors. Okay. Here, I forgot who this person is. Who is this person? I do not remember this person. I'm trying to remember now. It's not Chebyshev. Oh, is this? I think. Wait. Okay, I think this is Lobachevsky. This might be Lobachevsky. Okay, because I don't see any Lobachevsky integrals here. Yeah. Okay, Lobachevsky. I think this person's Lobachevsky. Lobachevsky. Very satisfying. However, I might have to put it with B, because, or, I'll put it back of A, because I will say a lot of the integrals do turn out nicer. But there are some times where it's like you have to manipulate the integral sometimes, and that can be a hassle. But it is a very satisfying. It is a very cool trick. Now I think about it, it's not as cool. It's not as cool as. I guess I'll leave it there. I'll leave it there as A. I'm sorry, but the Feynman technique, it's not as cool. It's cool, but it's like it's overrated. Maybe I can't say that, but it's just a lot of the times in Feynman Technique, it's exhausting because when you do Feynman Technique, the integral doesn't come out nice. Not all the time. I'm sorry. To all those Feynman Technique lovers, when it comes to speed integration, it's exhausting. This is Loophole Log. It's cool, but it's not as cool as Complexifying the Integral. So I'll put that in C tier. Mellin Transform. I honestly don't know too much about Mellin Transform and its properties. I might have to put it in D tier because you rarely use it. I mean, it's satisfying once you know it, like know the properties, but it's not like Laplace where it's like it has like a lot of nice properties. I mean, you could even count Ramanujan master theorem. Ramanujan master's trick goes with Mellin Transform with this, but it's not as satisfying. I'm sorry, it's not as satisfying. It's not as satisfying, right? You'll only use Mellin Transform when it comes to like generalization things like, I don't know, like this. Like cosine of x to the power of n. Like you'll never come across something like this. Well, you'll never come across integration problems with like special functions. Like Mellin transforms are only good for those type of stuff. So, in my experience, but with other nastier integrals, like you'll never come across that integration bee. So I'm sorry, but Mellin transform, it is a lot cooler than with any of these. It is a lot cooler. But it's not very satisfying. Okay. Norwegian Substitution. Oh, S tier. Norwegian Substitution. I'm sorry, but this might goes to S tier. This is so satisfying. This is super satisfying. For those, let's recap Norwegian Substitution, shall we? Right. Like let's be honest. Like how do you not find this integral cool? Like look at this. Tell me this is not a cool integral. Like come on. This is such a cool looking integral. Like tell me that this is not a cool integral. Like come on. How do you not find this very satisfying? Right? So this is Norwegian Substitution. Things like this. I love scaring beginners with this. I love scaring people with this integral, but it's a very easy integral, right? You divide everything by 4 to the power of x, you get 3x here, 3 over 2, 2x plus 1 here, and then this is just simply inverse tangent of 3/2 x ln of 3/2 plus c. Right. Let u equal 3/2 to the power of x for those who haven't seen it. Right. This is Norwegian Substitution. It's one of these tricks, and it gets spicier. Let me tell you, it gets so much spicier. Sometimes you'll get things like I'm trying to remember. Let's see. Something like, or let me look at. No, I don't have it. But things like this, like you have things like this ln of x, and then you do the this whole thing is like this or something, right? You let u equal this, and you do the whole u sub. I don't know, something like this. But it can get spicier, or it can get something like, you know, square root of like 3x. Like you can scare a lot of people with Norwegian Substitution. But if you know what it is, it becomes very satisfying, and the integrals are just simply easy. It just looks very cool and monstrous for those who don't know Norwegian Substitution. So, S tier. I'd say S tier. Laplace, Laplace can be a little bit of a hassle sometimes. So, but I mean, it's not too much of a hassle. So Norwegian Substitution. Oh, actually, I might go like that. Yeah, that looks nicer. I'm sorry. I find it more. It's definitely cooler than inverse jailbreak. I'm sorry. Is it cooler than Glass's master theorem? Yeah. Yeah. Now I think about it, I'm sorry. It really is cooler. It's a lot nicer, and it's like a friendly integration technique for everyone. Glass's master theorem, probably not for all levels. Norwegian substitution, absolutely, because it's just a type of U-substitution, and it looks very cool. Periodicity, satisfying, but is it the coolest? Probably not the coolest. I'll probably put it under the area of partial circle. Power substitution. I'll put it in C. I'll put it below. It's a lot nicer than complexifying the integral, but it's a hassle a lot of the times. Power substitution, it's either polynomial division or straight up just partial fractions or something nasty. So I might have to put it in C tier. Residue dodging. Oh boy, this is where it gets spicy. This one, it's hard for me to choose because I am very biased. Residue dodging, it's cool. I wish I could be part of the cool kids, but because I hate contour integration, because you're forced to know how to do line integrals or parameterize, like, I don't like that. I don't like that in speed integration because that's a hassle. So residue theorem sucks. I'm sorry. Residue theorem, I don't like it. But residue dodging though, residue dodging is very satisfying. Let's put it somewhere A tier. I'll put it at the back because you rarely use it. Or am I? No, I can't judge like that. It is more satisfying. And it is more cool. It's not as cool as constructive Feynman. Somewhere along here with constructive Feynman Technique. I'll put it here. It is cooler, I would say. Just a little bit. So difference between residue theorem and residue dodging is, like I said, residue dodging, you don't know what you're doing. You're just kind of you're kind of pretending and fitting in with your opponents, right? However, it sucks because you can't always do it. So like a good example, like if I'm given like cosine of x, like let's say like examples like this, right, from 0 to infinity, then I'll be like, oh, residue dodge, use residue dodging, gotcha. 2 pi times 2 residue of like z equals, let's see, what's this is going to be e to the ix, or I'm sorry, e to the z, e to the iz, right? So it would be like residue of e to the iz. So pretty much you're pretending. You don't know the actual full residue theorem, but you're just kind of pretending, you know? And so you're like, okay, so this is like what, from 0 to infinity. Or let's make it more realistic. From negative infinity to infinity, right? Now we have like r, negative r, this whole contour that goes like this way, right? And then from the denominators, let's see, we have like, we know that z can't be I, and I is right here. 2i, can we have 2i? Possibly. Can we have 2i? Probably no, because r is infinite, so maybe we do have to take into consideration with. Okay, so you get like the sum for like z for like I and 2i, right? The negatives, they're like down here, but like they're not inside of the loop, so you don't have to worry about those. And then you just plug in the limit, right? Substitute for the limit whatever. I'm sorry, with the limit. I don't know, whatever. I'm writing the notations very badly, but it's like you just do this whole limit thing. Okay, whatever, and then you end up with like pi e square something, whatever, along those lines. That's residue dodging. You're pretending to know what you're doing, and you just go by the residue theorem formula. Okay, that's residue dodging. However, it doesn't always work, because sometimes you'll be thrown with like an Arabic style integral like this, like ln of x, x4 plus 1. Okay, now you can't do residue dodging. You can use residue theorem, but you can't do residue dodging, right? Because you actually have to know what you're doing to solve this, right? You have to know your contour path. It might look something like this, or like some nastiness. I don't know, whatever. You can't actually do that. This is from 0 to infinity, so it would be more like this graph. Yeah, and you don't utilize this because this is ln of x, so you have to be very extremely careful because you can't have negative numbers inside of a logarithm. Not even complex either. So you have to be very careful with your contour, something, I don't know. Some nastiness. Okay. I don't know. I know nothing about complex analysis, unfortunately. And it's hard for me to learn contour integration because I'm not comfortable with parameterizing and contour integration. It is hella puzzling to do residue theorem. So, unfortunately, you can't always residue dodge all the time. Only a small amount of integrals you can residue dodge. It's a very cool integral, it's very satisfying. So it is, I would put it in A tier, next to constructive Feynman. So that's residue dodging. Okay, reverse product rule, that's satisfying. Probably put it, it is definitely more satisfying than Weierstrass. I'm sorry, Weierstrass this can destroy itself. This is nasty. The 1 plus sine 2x trick. Ooh. It is nice. Probably put it here. It's nice. Square technique goes along with 1 plus sine 2x. It follows the same structure as 1 plus sine 2x. Trig identities wise, trig manipulation wise, I probably would say 1 plus sine 2x is more satisfying. Actually, no, I lied. Because the square technique is, the integral is cleaner. The integrals are cleaner, so I'm going to have to go with the square technique being more satisfying. But it's all B tier. Not as satisfying. I guess it is cooler than the reverse product rule. It is cooler than the reverse product rule, but it's not as satisfying as periodicity. Oh, here it is, the secret trick. This is what it is. With Korean substitution, I might have to put it in A tier. Yeah. I'm sorry, but it's cooler than Feynman Technique. I'm sorry. Semi-integration by parts. Oh, I actually like this trick. I might have to put this with A. I just realized I put forced U-substitution here. Forced U-sub, it is more satisfying. Symmetry Queen's Rule, Advanced Trig-Substitution. I'm gonna put it here. It is more satisfying than any of these. I'm sorry. It's because things like this, like advanced techniques, it's like it becomes a hassle. It's exhausting. Forced U-substitution, or these right here, is like the integrals will always be nice, a lot nicer. So geometry, utilizing geometry. Things like absolute value integrals or the min and max, geometry type graphing, lame. I'm sorry, it's lame. No one likes graphing. Okay, I don't care what you Olympiads says. The graphing sucks. This is Taylor series. Yeah, using Taylor series. Ooh, I might I honestly do enjoy using Taylor series. Probably more than... I might have to go up here. It's not S tier because the integrals can be a hassle. So I might have to go... probably put it up to here. It is definitely cool. It's super cool to use Taylor series. Yeah, I'm going to put it up here. But it's not as satisfying. It's not as clean as Queen's rule. So put it up there. It's super nice. Very nice. Now I have to think about it. Symmetry. Symmetry is cool, but it's I do find it a lot more satisfying than the others because it's so much cleaner. These like advanced techniques like this, like it's a hassle. Like they get the integrals. Yeah, the technique is cool, but the upcoming integral you get is disgusting. So I'm sorry, but Symmetry has a lot nicer integrals. Even though it's simple, it's super simple, but the integrals for speed integration is just a lot nicer. And that adds into the satisfaction. Woo! Let's start with this one. Converting. This is just pretty much trig manipulation. It is satisfying. I'll put it right here. Not as satisfying as complexifying. This is Undertow Technique. This is the one I explained. Similar to Caveman. It's satisfying once you know it, but if you don't, it's disgusting. So I might have to put it with Caveman. It is a lot more satisfying than Caveman Trick. A lot more satisfying than Caveman Trick. Wallis Trick. Wallis Trick is nice. I'd say more than the gamma function. Yeah, more than the factorial formula. But it's not the coolest. Not the coolest. Then the zero substitution. This is just an algebra trick. This is it's not that cool. it's cool for beginners, but once you know like up to like a beginner speed integrator, like it's like alright, everyone knows this trick. Okay. Alright, now we're down to the last two that I've never shown you before. Let's start with the treble clef. Treble cleffing. Treble clef is not really a technique. It's more of a signal. It's a speed integration signal. That's pretty much what it is. It's more of a signifier. So pretty much when it's whenever you have something like, let's say, x square, x minus 1 square, x minus 3 square. Okay? Let's be very real. Like, I don't want to do partial fractions with this because this takes forever. Okay, doing this and then doing the same thing for the other side, it takes forever. I don't want to do that. Okay, no. So instead, we're gonna treble clef this. So, in other words, you're solving the square version of this. Okay, and then now this is you just do Heaviside. Right, this is what? 1, this is -2, 1, 3, this is like 2, right? And then so now turning it back to a regular integral, this is just simply, I'll turn this into like 1/4. I'm going to factor out the half. So it's 1/4. And then what you have is x minus 3 of 3 minus 1 of x minus 1 squared. So that's all that equals. So that treble clef is just a signifier. And this is so much easier because it's like, this integral is equal to 1/4. Square this, we know how to do that, right? This is an easy integral. This is an easy integral. Okay, but what about the middle term? I'm sorry, that should be like minus 2 and then, let's see, 6? Of x minus 3, x minus 1. But like, we already know, no, we don't. This is different. It's a different. partial fractions. But if this was like 1, then you could just reuse that. But because this is x, we have to do Heaviside again. But that's okay, right? Because we could quickly do Heaviside on this. And so that's treble cleffing, right? Rather than doing this whole nasty partial fractions, you just square it. And this is just to signify that what you're doing is not the original integral, it's the square version. Okay? So that's just treble cleffing. It's just a speed integration trick. I don't teach it because, like I said, in integration bees, you'll never come across an integral like that. Ever. Like, very rarely. So, but it's nice. It is satisfying, but it's not as satisfying as British Substitution, or these, Ahmed and Coxeter's. So, I'm gonna have to put it here with B tier. It's nice. It's very nice. It's very satisfying, but it's not as cool as one of these. Okay. Or maybe it's not as cool as British Substitution. British subbing is very cool. Alright. This one. Tidu's Doppelganger Trick. This one is also another one I have not shown you. But let me first rate this. Tidu's Doppelganger Trick. It's a very cool trick. I genuinely want to put an S. But the thing is, the integrals you get is disgusting. So I might have to put it... It's such a cool technique, but... Oh, man. The integrals are nasty. So, because of that, I might have to put it... It's definitely cooler than force U-substitution. But it's nastier than Taylor series. Yeah, I'm gonna have to put it like that. I think that seems fair. Let me show you what Tidu's Doppelganger Trick is. So, Tidu's Doppelganger Trick is a technique by Tidu Andreescu. And let's say you get something like... Let me look at my notes, because there's a specific way to do it. So a good example is like... So the purpose of this technique is to find the doppelganger, not a clone, but a doppelganger of this integral. So this equal to I, okay? Then J is going to be the doppelganger integral. Okay, so what's our doppelganger? We will create our doppelganger, square root of x minus square root of x minus 1. This is our doppelganger. And now you're probably thinking, okay, but like, why would you want to do this? It's because we are solving for this, right? So would it have been nice if we add these two together, I plus j, I minus j, and then when we add these two integrals together, we want 2i, right? The reason why we want j is because if you realize, if you add I and j, okay, if you add these two radical functions, they can cancel each other out, right? If you've seen this Olympiad trick, right? If you square it, you get like what, 2 square root of x, and then plus 2 of the square root of x minus. Oh wow, yeah. So this is just 2, right? And now look at, you just simplified it. All right, square root it back, and now this is like square root of 2 times square root of x plus 1. So that means that this whole thing equals to this, right? And it's so much nicer, right? And oh, would you look at that? You know, I plus j is equal to the integral of what? 1 over root 2. And you have like 1 plus square root of x. 1 plus square root of x. Oh, this is equal to dx of the square root of 1 plus this. Oh, force U-substitution. Oh, this is an easy integral now, right? And then you do the same thing for minus, right? You do the same thing for minus, and this is like negative version. So this is like a negative version. However, it's a lot. This is a bad example, I'm sorry. But it would be it would be nastier. This I minus j would be a lot uglier to deal with because you have 1 plus x, but then you have like I'm sorry, why am I doing root? This should be root 2. Yeah, this should be root 2. Root 2 on top. And then you have square root of x minus 1. And then you're just gonna have to deal with this integral. But that's Tito's doppelganger trick. Is you find a doppelganger and you use this process to find the integral itself. Okay? And you just cancel out the doppelganger. The doppelganger is just to help you find easier integrals to manipulate with. Okay? So that's Tito's doppelganger trick. And like I said, it's a very cool trick, but the integrals is disgusting. Like this one, like this is a disgusting integral. So it's cool, but it's not entirely satisfying because the integrals are nasty. So, and it sucks to do it in speed integration sometimes. You just have to be very, very lucky. So, and I don't teach it because you'll never kind of come across that in integration B, or very rarely, super rare. So like it's something that you don't have to be too focused on. So Tito's doppelganger trick, I will put it A tier because it is extremely cool. Just not entirely satisfying because of that disgusting portion of the integral. Okay? It's super hard to find a very nice integral with that trick. But other than that, that is the... Oh, no, I'm not done yet. Ooh, there's one more. There's one more that I forgot. I'll put it here. But there's one integral trick. It's not exactly an integration technique. It's more of a numerical. Like let's say you're told to do this, and they want you to approximate it as close as you can, or they want you to solve something like this and be as close as you can, or whatever, etc. Right? So there is this technique that I call weaponizing the integral, right? Because we can't use Taylor series because this is disgusting, right? I mean, you could, but then it's going to look like e to the x in terms of, you know, and this still is, it's not helpful. This is still not helpful, right? This is still not helpful. I mean, unless you do like this, I guess. Oh no, it's mid. X and yeah, 1 plug in 1. 0 minus 1. I think that's what I would get. Yeah. Okay, you can approximate it, but like you have this e. That's nasty. You have to simplify all whatever. I don't know. Maybe this is an easier version. But there's a trick called weaponizing the integral. Weaponizing the integral is whenever you deal with something nastier, like let's say like 0 from 2 pi tangent of cosine of x, or what is this from pi over 4, whatever. Approximate it, right? So there's this like child prodigy, or I don't know. He is currently in undergraduate, but his name is Glenn Bruda, and he came up with this. I don't know if he came up with this during high school or undergraduate freshman. But somewhere along those young years, like this man is crazy. But pretty much what you do is you weaponize this integral. And the process of weaponizing this integral, there's a formula, but the formula is long. So I'm just going to show you the process. But pretty much you take the Taylor series of this. You take the Taylor series of a function. I think he generalized it. Let me go like this. So whenever you have like a nasty... let's say a nasty function. You find the Taylor series of this. You find the Taylor series of the function. But this person manipulated it in a way where it equals to like this integral equals like a Taylor series of f of x. Oh, something I forgot. I need to look back at it. But you turn this into some sort of... I'm doing this wrong. I'm trying to remember. It's a very complicated process. The Taylor series of this function is like x or something, and then the person manipulated the equation to like 1 is equal to x f of x, or some sort of Taylor series, whatever. But pretty much you use Taylor series, and then what you do after that is you use integration by parts. And what that does is it turns your whole sum with a bunch of pi products with like dn derivatives, however many times you did the Maclaurin-Taylor series or whatever. But you get a pi product. I don't know what I'm doing. It's something like that. But the tail of the whatever approximation, one of these, I don't know. But like the tail, you get to ignore them, and then you just follow along with like, oh, okay, this is approximately, equal to this based on these first few terms, and then you get a more accurate result with like ugly functions like this from 0 to 1. Oh, approximate this, and then you use Glenn Bruda's weaponizing the integral trick. Okay, there's a paper. I'll put it in the description. There's a paper for it. It's very, very cool, but it's scary. So weaponizing the integral, I would probably put it. It's cool, but it's nasty. So I'd probably put it in C tier. I'm sorry, Glenn Bruda. Don't hate me on that. But it's a very cool trick. It's just nasty because you have to do Taylor series and you have to do integration by parts, and that can get annoying. And you keep doing integration by parts recursively until when you get to like the tail terms that we don't really care about because they're like decimals. So just to recap, weaponizing the integral, you use this and then you do integration by parts, and you keep doing it, and you keep doing it, and then whatever these are, we can ignore it because these are like tail terms, and so you just use these answers to approximate the integral. So that's pretty much weaponizing the integral. That's the whole idea, but I don't remember how to effectively do it. But like I said, I'll put a paper in there. But yeah, genius. But other than that, here it is. This is the whole tier list, in my opinion. Yeah, I'm sorry. Norwegian Substitution is very cool, very satisfying. Glasses Mass Theorem, Inverse Jailbreak, and Laplace. Alright, so that is my tier list for the coolest and the most satisfying speed integration tricks. Okay? If you want to share your thoughts on it, I'll put a link into the description as well for this tier list. Okay? Alright, that's it. Hopefully I don't cause any rage of opinions in the comments. Hopefully. But yeah, this is just for fun. So thank you guys so much for watching, and I'll see you guys in the next video. See ya.